focus on the classification of entire graphs. So what I'm going to do in some sense is to follow the first two lectures in the following sense. I'm going to use the sister correspondence that Benoit did in the first lecture, and I am going to use the theory of harmonic maps into the hyperbolic plane, just as Logan did in the second lecture, in order to prove some results in this theory of CMC surfaces in homogeneous manifolds. So let me recall that in Euclidean space, you have this correspondence of H equal to 0 in R3, R correspondence to H equal to 1 in H3. And by the correspondence of Benoit, you have something similar in these homogeneous spaces. H equal to 0 in Heisenberg space correspond to H equal to 1/2 in H2 cross R. Okay, so it seems like the theory should behave the same way. And moreover, we have seen, just as here you have a conformal Gauss map, here we saw in my previous lecture yesterday that you have a harmonic Gauss map for that theory. Okay, so it seems like this theory here should be in some sense similar to this surface theory here. Okay, so in some sense there are many other things that should work from this analogy, but we are going to focus today on one which is not like this, and it has to do with the Burstyn problem. So let me recall, well, the Burstyn theorem. The Burstyn theorem is very classical. It's one of the most oldest results in minimal surface theory, global results, and it states that if you have an entire minimal graph in R3, then it must be a plane. Okay, so essentially you don't have entire graphs, only planes. So this question this theorem had a deep impact into the theory of PDEs and also into geometry in both cases. So we can talk about the Burstyn problem in any other theories. And it turns out that in the case of homogeneous manifolds, this makes sense in the sense that we have, as Benoit said in the first lecture, a structure with respect to a projection. Okay, so all of these spaces are fibrations over a space of constant curvature. That is, you have a canonical fibration from E3 kappa tau into the space of constant curvature two-dimensional M2. So this acts like a projection, and so you can claim simply that define an entire graph to be a surface such that its projection onto the base space of the fibration is a diffeomorphism, a surjected diffeomorphism. Okay, so this is the natural definition that you can put here. Moreover, the vertical field is a Killing field, so you can do translations along the vertical direction. So everything works exactly like in R3, and this is the most natural definition. So, inspired by this Burstyn theorem, you can study the Burstyn problem for CMCH graphs in these spaces. So you wish to classify all the entire CMCH graphs in here, okay? And for the special case where you have mean curvature equal to 0, that is minimal surfaces, we shall refer to this problem just as the Burstyn problem. We will not specify the value for the mean curvature, okay? So, by this analogy, the problem, well, the purpose will be to classify the entire graphs of critical constant mean curvature. Let us recall that critical constant mean curvature means this. Okay, the mean curvature square is minus kappa divided by 4 in this space. In particular, you have these two examples that I wrote there, like H equal to 1/2 in H2 cross R and minimal surfaces in Heisenberg space. So why is it natural to use this special, to try to classify this special value of the critical mean curvature? Well, as we said, the critical mean curvature is a value that comes out because it is the first value where compact examples fail to exist. Well, it turns out that it is also the first value in which you have entire graphs in the following sense. Assume that you are that you have an entire graph in some of these spaces. Then it turns out that if this thing h squared is greater than minus kappa over 4, then you don't have entire CMC graphs. Okay. Well, to be honest, you would need to say that if you are in S2 cross R or in Berger spheres, the entire graphs are slices. Okay, so you have to consider that case, but they are like trivial examples. You can more or less say that there are no entire graphs here. Why is that? This is so just because of the maximum principle with respect to spheres. Let me explain this in H2 cross R, which is maybe the place where the space where it is better seen. So assume you have a graph like this, an entire graph with h greater than 1/2. Okay, for a certain value, h greater than 1/2. Okay, so but we know that there are rotational spheres of any value of the mean curvature greater than 1/2 also. So you could place inside the mean convex part of this graph, you could place a rotational sphere whose mean curvature is exactly this value of h. Okay, then you translate it until you have a first contact point, and this is a contradiction by the maximum principle. So that's it. Okay, and this works actually for all the other spaces. So it's clear from that you cannot have entire CMC graphs. So this is the first point where you can say that there are, and so it's natural to put the Burstyn problem here. Okay, and so the situation will be actually that we will be able to classify all these entire graphs for this value of critical constant mean curvature. Okay, which is in some sense a bit surprising. Let me say that for the case of CMC graphs, okay, if you see the CMC condition as a graph, you have an elliptic PDE in divergence form in general. Well, not in this case in divergence form. You have a CMC equation, an elliptic CMC equation. Okay, so how can you do this? You take the model for the space, as Benoit said in the first talk. I mean, if you are with H2 cross R or with PSL2R, you take the disk cross R, like this thing, but also for PSL2R. And in the case of R3, Heisenberg, or Berger spheres, you take R3, where in Berger spheres, as Benoit said, you need to take off one fiber. Then you put this metric, which is called, in some senses, Cartan-Franceano metric, which is the metric of the homogeneous space. So you can compute the CMC graph equation, and it turns out that is this funny expression here, which depends on x, on y, on kappa, on tau, and on the derivatives of the function, first derivatives of the function, which are here again derived, so you have second derivatives. Okay, this equation is taken from a paper by Hujoli, so you can ask him for the details in case you want to see how it's done. Okay, so we can consider as a particular case the case of minimal surfaces in Heisenberg space. That is, in this equation, we put here a 0, and we take kappa equals 0. So this delta is a 1. Okay, so we can rewrite this thing, and it turns out that you have the following equation. Okay, you have the following equation here. Okay, the equation turns out to be very simple here. You have 1 plus beta squared fxs minus 2 times alpha beta fxy. Well, this thing where alpha and beta are given by these expressions here. Okay, for that, okay, the problem here, the Burstyn problem, is to try to classify all the entire minimal graphs. So we wish to classify all the solutions to this elliptic PDE that are globally defined for every value of x and y. That's a problem. Okay, so why is this problem especially interesting in the case of Heisenberg? Well, it turns out that if this constant, which is in general a positive constant that can be assumed to be 1/2, for instance, you make it go to 0, then this tends to disappear, this tends to disappear, and in the limit case tau equals 0, you get actually the minimal surface equation, the classical minimal surface equation. So the Burstyn problem in Heisenberg tends to the Burstyn problem in R3. This is not, I mean, this is not surprising, because when tau gets 0 here, you have the Euclidean metric, right? So, I mean, but the thing is that in some sense we are perturbing the classical Burstyn problem in R3 into the context of Heisenberg space. So in some sense it would be natural to think, okay, as in R3 you only have planes, maybe in Heisenberg you will still have only planes, because R3 is like a limit situation. Okay, so starting with this, from this point of view, several people started working with entire minimal graphs in Heisenberg space. It turns out that planes, planes are also solutions to here. Okay, so you have that planes are solutions to the minimal graph equation. So this works like in R3, but then you see a first difference, and is that if you start looking for surfaces that are invariant under hyperbolic translations, you end up seeing that you have also saddle type surfaces. This is a solution to the equation of minimal graphs in Heisenberg, and more generally you can put here a constant and all these fun expressions here with depending on y, and it's still a solution to the Burstyn problem in Heisenberg. So I mean, this is just the first example that come out, and it makes a difference with the case of R3. Okay. So the first question was actually whether those examples were the unique examples. Like, okay, maybe in Heisenberg, apart from planes, you have this, and that's it. Okay, but this is not like this. Well, for instance, because Benoit Daniel constructed, using the Gauss map of minimal surfaces in Heisenberg space, some other examples of entire minimal graphs which were not invariant by a one-parameter group of isometries of the space. They had some symmetries in the sense that they are Fouriered by straight lines, and they are explicit, but they are not like these things. So one starts to believe that the space of solution to this Burstyn problem should be very large, and that only these examples were known basically because you need to solve a difficult partial differential equation, and so you are not expected to have a lot of solutions, of explicit solutions. Okay, so in this talk I'm going to show how the Burstyn problem in Heisenberg can be solved. How I'm going to do this? In some sense, I'm going to use the same idea that Logan did in the first talk for proving the structure theorem for finite total curvature minimal surfaces in H2 cross R. What I'm going to do is to use that you have a harmonic Gauss map into the Poincaré disk, and to use the whole analytic theory that many people have been developing for this particular case. Okay, so let me say that well, I'm going to start with the case of H2 cross R. Okay, so recall something we did yesterday, and is that the construction of a hyperbolic Gauss map. I skipped this slide in the previous lecture because I was running out of time, so I'm going to explain it now. I defined the hyperbolic Gauss map in H2 cross R yesterday by putting it into the Minkowski force space and doing some computation with the light cone of the space. It turns out that you can actually view the Gauss map in H2 cross R using a somehow funny procedure, which is the following thing. Assume, how do you define this? Assume that you have a surface in H2 cross R, any surface, okay? So, and you assume it is a local graph. This is necessary for everything that we are going to do. It is local graph over the projection. Hence, you can orient it so that its unit normal points upwards. So you do parallel translation to this point, to the base point here, and and parallel translation of the unit normal. And then I create here, this is H2, okay? So I create here a Poincaré ball model so that H2 is totally geodesically contained in this H3. And now I can use the usual hyperbolic Gauss map in H3. That is, I take these initial conditions and I take the unique geodesic in this model that reaches the boundary orthogonally here. Well, it should be more orthogonal than it is, maybe, but okay. And so this gives you a point from the surface to this upper sphere at infinity. As this always points up, this is just the upper half sphere. And finally, what I do is to, so I take a point in the upper half space, half sphere, like x0, x1, x2, and I put it in correspondence with the point. I divide it by the first coordinates, x1 divided by x0, x2, sorry, it's the other way around, x1 divided by x2, I put here x0 to be positive. That's the upper, well, x2 to be positive maybe. So I can put here x0 divided by x2, x1 divided by x2. Okay, so what I'm doing is just to project like this. And so in the end, this turns out to be the projective model for the hyperbolic plane. Okay, so this is an explanation of how it works. So the hyperbolic Gauss map here is the whole composition of this process and takes values finally in the hyperbolic plane. Okay, this is the claim model. Okay, so as we said yesterday, it turns out that surfaces with mean curvature 1/2 in H2 cross R, for them, this hyperbolic Gauss map is harmonic. And moreover, its Hopf differential, which is a holomorphic differential associated to any harmonic map, is actually minus the average Rosenberg differential. Okay. Some other things can be said about this type of maps. Let me put a definition here. Assume that you have a harmonic map into a Poincaré disk, into H2 that we view in the model of the Poincaré disk. Okay, so this is a subset of the complex plane. So we say it is nowhere anti-holomorphic if Gz is different from 0. Okay, if Gz was 0, it would be anti-holomorphic. We say that Gz is anti-holomorphic if this condition holds. And if this condition holds, we can define this metric here, which I would call the partial G metric. Okay, I'm not explaining this why this comes here now. I will explain it afterwards. But it turns out to be a metric because this thing is different from 0. So this turns out to be a Riemannian metric. And we will say, for a nowhere anti-holomorphic harmonic map, we will say that this pair, made up by its Hopf differential and its partial G metric, is a pair of Weierstrass data for the Gauss map. So this definition is relevant because of the following fact, and is that if you start with an H equal to 1/2 surface in the product space H2 cross R, then its hyperbolic Gauss map always admits Weierstrass data. Its Hopf differential is minus the average Rosenberg differential, and the partial G metric associated to the hyperbolic Gauss map has a very simple expression. Is the angle function square. Remember that nu was the last coordinate of the unit normal. Okay, the product of nu was the product of the unit normal with the Killing field of the ambient space. In H2 cross R, just the x3 direction. Okay, so this is the other thing is nu square multiplied by the conformal factor of the metric. We will see that this thing here, which is different from 0 since we are always working with local graphs, this thing here will be special for a lot of things that I'm going to explain in the talk. Okay, there will be this contains a lot of information on the surface. These two things. Okay, so my idea is to use harmonic maps in order to understand the geometry of H equal to 1/2 surfaces in H2 cross R. I know that the hyperbolic Gauss map is harmonic. Now I need to go for the converse. Okay, can I recover any H equal to 1/2 surface in H2 cross R in terms of its hyperbolic Gauss map? Well, it turns out that once you have this, the rest is simple. It's just some computations dealing with integrability conditions, working a bit, but it's quite standard, the following result. Assume that you have that you start with a harmonic map into the plane and has Weierstrass data where it's Hopf differential and the partial G metric, which I call it here tau 0. Okay, and I assume that it is not totally singular. That is, that the image of the Gauss map is not one-dimensional. In that case, it would be actually one can compute, and it would be a very specific family of h equal to 1/2 examples invariant by hyperbolic translations. So I rule out this case because this is known, and I start working with the rest of the cases. Then for that harmonic map that I prescribed, there is exactly a 2-parameter family of surfaces with h equal to 1/2 in this space H2 cross R, whose hyperbolic Gauss map is the harmonic map we started with, we prescribed. Okay? And moreover, as it is like this, by the above computation, all of them have the average Rosenberg differential minus q this square, and they satisfy that its partial geometric is lambda multiplied by the square of the angle function. Okay. So there is a, given the average Rosenberg differential, I have at least a 2-parameter family of examples like this. And moreover, the immersion can be recovered in terms of the Gauss map in the following sense. Here you have a funny expression that is not very interesting, and you have here the height function. In this expression, you have 3 things involved: the Hopf differential, the tau zero metric, and the height function. But the Hopf differential and the tau zero metric are already known in terms of G, so these are known objects. So you still need to see what's H in order to see that you can describe everything. And this height function H is actually a solution to this system of PDEs that you have here. In this system, all the coefficients, you have H, which is the unknown thing, and the coefficients are again tau 0 and Q. So you can, just by the Gauss map, you can write this system. Okay, so the problem is whether this system has solutions and whether you can find such solutions. Well, it turns out, I will say afterwards how to solve this system, okay? Not now, but I will say afterwards how to solve this system, which is the system for the height function, okay? But it turns out that you can, if you prescribe the initial condition, this system always has a unique solution, and this is a consequence of the harmonicity of the Gauss map. And you can prove also that solutions associated to different initial conditions produce different surfaces in H2 cross R which are in general non-congruent. So starting with a Gauss map, I have a 2-parameter family of in general non-congruent surfaces with the same Gauss map, let's say. Okay, and moreover, by the construction from the very beginning, they are all local graphs. The reason is that, as I said previously, in order to define the hyperbolic Gauss map, you need the surface to be a local graph. You need the unit normal to point upwards. So all of them will be local graphs. Okay, so because of this is a complex thing. Okay, this is a complex initial condition. So for each initial condition, you have a different solution, and it turns out in the previous thing that I mean, once you have that initial solution, you put it here. The solution here is different, and you can prove that they are not isometric. So in some sense, well, in some sense, is this initial condition what is giving you all the information? I mean, it differs from the case of R3 just because of the number of isometries of the ambient space. For instance, in R3, you have the Gauss map, and the Gauss map recovers the surface, but it recovers it uniquely. Why is that? It's because the isometric group of R3 is of dimension 6. But here in H2 cross R, the isometric group is only of dimension 4. So in some sense, you are losing 2 isometries. And these 2 isometries that you are losing are the 2-parameter family of non-isometric things that you obtain. It's more or less the rough idea, okay? Okay, so now I know how to describe surfaces of H equal to 1/2 in H2 cross R in terms of harmonic maps. Why is this relevant? And they are local graphs. So this is very good actually for the Burstyn problem, because Burstyn problem deals with graphs. So I mean, we are not losing information there. So how can I come from the H equal to 1/2 case to all the other cases of critical constant mean curvature, and in particular to the case of minimal surfaces in Heisenberg? Well, this is by the loss on type correspondence that Benoit explained in his first talk. Well, in his first talk today, second talk of him, I mean, at 9:30, okay? Benoit explained that you have a correspondence between simply connected CMC surfaces belonging to different homogeneous spaces E kappa tau. And the resulting sister surfaces, for the resulting sister surfaces, you have some preserved quantities. One is the induced metric, so the surfaces are isometric. Okay. The second one is that they have the same angle function. So in particular, this is important because if the angle function is different from 0 for one, then it is different from 0 for the other. So it preserves the property of being transverse to the Killing field. Or in other words, it preserves the property of being a local graph over the base space. Okay? And on the other hand, the average Rosenberg differentials differ, well, this is not correct, not up to a sign, but up to a constant. Okay? And finally, it preserves the property of having critical constant mean curvature. So what I'm going to do is to use this Lawson correspondence together with the knowledge that I have on the Gauss map of H equal to 1/2 surfaces in H2 cross R in order to solve the Burstyn problem for all values of the critical constant mean curvature. So let me state it first for Heisenberg. As we said previously, in R3 you only have planes. What happens in Heisenberg? Well, the solution is this thing. Assume that you start with a holomorphic quadratic differential on the complex plane or on the unit disk, which is not identically 0 in the case it is parabolic. Then you have a two-parameter family of entire minimal graphs whose average Rosenberg differential is the holomorphic quadratic differential we started with. And conversely, any entire minimal graph belongs to the family given by the existence. Okay, so this is the solution. Okay, some comments about this solution.
When you take the initial value equal to 0, is that backward?
Sorry?
When you had the previous problem, you had pick an initial value.
No, it's just no, it just means because the initial value. I mean, you need to fix a point. I mean, you do all the things at a point. So this would be telling you maybe that the point is you have tangent plane vertical at one point, but that doesn't mean too much. Okay, so the case where the average Rosenberg differential equals 0 and sigma equals c, which is the case we are excluding in this theorem, is because it is a vertical plane. Okay, so it's not a graph. So we are excluding that point. Okay, so this is not realizable as the conformal structure and the average Rosenberg differential of any entire graph. The theorem says that apart from this, you can realize all holomorphic quadratic differentials. So the existence part is telling you that there exists an incredibly large amount of entire minimal graphs, a two-parameter family for each holomorphic quadratic differential. So it's extremely large. So one could say, okay, it seems pretty unreasonable then to obtain explicit formulas for all the graphs because it's a general family. Okay, so the most natural thing that one can say is, okay, I want to describe all the solutions in terms of some specific known class of objects. And this is what the theorem, the uniqueness part is telling you, and is that you can classify all entire minimal graphs in Heisenberg in terms of the space of holomorphic quadratic differentials on the plane or on the disk, which is a well-known class of objects. So that's why the theorem, in some sense, can be seen as a solution to the Burstyn problem. Of course, this is not telling you, for instance, anything about the asymptotic behavior of the example, which is a very interesting question, or some other properties that one might see, but you have a very clean classification theorem. Okay, once we do this, I think I was going to say something. Well, once we do this, it turns out that the same theorem is true for every value of the critical constant mean curvature. So any holomorphic quadratic differential as before, then you have a two-parameter family of entire CMCH graphs with critical constant mean curvature, whose average Rosenberg differential agrees with the holomorphic quadratic differential we started with, and the converse also holds. So you are not solving Burstyn problem just for minimal surfaces in Heisenberg, but for all values of critical constant mean curvature. In special, you are solving it also for the case of H equal to 1/2 surfaces in the product space H2 cross R. Okay, to this result, several authors have contributed in several ways. So I'm going to try to explain this because at the same moments, more or less, we were several people working on the same subject, so it was like one people obtain something, the other people obtain some other thing. So I'm going to explain this a bit. The first thing was existence. Existence first, I did with Isabel Fernandez a general result proving that there exists a certain family of candidates in null spaces that were local graphs and complete, but we didn't know that they were entire. Okay, so in terms of quadratic differential, so that was the first step. Afterwards, the problem was to prove that they were entire to see that they are solutions to the Burstyn problem. Then Logan Hausbith, Harold Rosenberg, and Joel Spruck did it in H2 cross R using a different technique that maybe Benoit is going to talk about in his last 2 lectures, but I'm not going to talk here. And a bit later, we realized that you can prove that all of the examples that we knew that we didn't know that were entire graphs, they are actually entire graphs by a very simple argument that I'm going to explain next. As regards uniqueness, in the case of Heisenberg Space, we did it in the first work here. We proved that this converse part. And for the rest of spaces, using a very deep argument relying on a theorem I'm going to explain afterwards, Benoit Daniel and Laurent Hausbith were able to prove all the remaining cases, not just Heisenberg, but to solve the Burstyn problem in all the remaining spaces. So this is more or less the story of the topic. So let me explain first. Existence is much simpler than uniqueness. So let me explain first existence and saying what I call canonical examples. So this is the assertion for existence. Any quadratic differential, holomorphic, can be realized at the average Rosenberg differential of a 2-parameter family of entire graphs. Okay, the key is a result by one and out that Laurent talked about in his first lecture. The theorem of one and out can be stated as follows. Assume you are given a holomorphic quadratic differential in the disk or in the plane. Then you can construct a harmonic map from the Riemann surface sigma into the hyperbolic plane such that its Hopf differential is the quadratic differential we prescribed, and moreover its metric partial G is complete. Okay? So the completeness here, and moreover this harmonic map is unique up to isometries under these 2 conditions. So I mean, this is a quite deep theorem by one and out. So what I'm doing now is to use the fact that I have a harmonic Gauss map into H2 cross R in order to take this result and apply it to surface theory. So I consider now from Q, from the Q that I'm given, I consider the harmonic map given by the one-out theorem. And from the harmonic map, I can consider the 2-parameter family of examples in H2 cross R with H equal to 1/2 given by the representation, harmonic representation formula that I described previously. Then it turns out that, as it said in the theorem, the metric partial G is actually this expression, the angle function square multiplied by this thing which is the induced metric. Okay, so as the theorem of one and out says that this metric is complete, it turns out that in my surface in H2 cross R, this metric is a complete metric. Okay. In particular, as you have that nu square is less than or equal to 1, you have that nu square dds square is smaller than or equal to dds square. Okay. So as this metric here is complete, the induced metric of the surface in H2 cross R is complete. So we are talking about complete examples that are local graphs. The problem is whether they are entire. And let me say also that this metric here, is preserved by the sister correspondence. Why? Because we said that the correspondence was isometric and was preserved in the angle function. So this thing is preserved. So this is true not just for h equal to 1/2, but for all other values of critical constant mean curvature. So I'm going to prove now that this metric is not just less than or smaller than the metric of the induced metric of the surface. I'm going to prove that the metric is smaller than the metric of the horizontal projection onto the base of the surface. Once I prove this, imagine for one moment that I can prove this. Okay, that this metric is smaller than the metric of the horizontal projection. Then, as this is complete, the metric of the horizontal projection will be complete. But this means that if I take the map from the surface to the horizontal projection, the map actually is preserving distances if I take the pullback of the metric, and the space where I'm going to explain this. Okay, I'm going to explain this carefully. Assume you have a surface into this space, and consider now the canonical fibration here. If you consider now this canonical fibration, then I can do the composition of two things. I can define capital F to be the map of the surface composed with this canonical fibration. So we have a map here from the surface into the space of constant curvature kappa. Okay. So assume I can put on sigma the metric g of f, which will be defined just as the pullback by f star of the metric of f to k. Okay. Okay, as this is a local diffeomorphism, I can do this, and in that case, f becomes a local isometry. What I say now is the following thing. Assume that this thing is complete. Okay. Assume for one moment that you have this inequality. Then, as this is complete, this metric is also complete. So this is actually telling you that this is a covering map, and as this is simply connected, it turns out that f is a global diffeomorphism. Okay, so f global diffeomorphism, so the surface is on an entire graph. So that's just a covering space argument, very simple. Okay, so the big point here is to prove this estimate. If you prove this estimate, you are proving that all the sample we have constructed are indeed entire graphs. Okay, now how can you prove this estimate? Well, it turns out that it's quite simple to prove the estimate. Let us assume that we are working in these conditions, right? In these conditions here. So if I take Z to be a conformal parameter, for the immersion C, this means two things. That the product of Gz equals 0, and that the product of Gz bar equals lambda over 2. Okay. But now from here I can go to the metric I wrote there, to the GF metric, and this is just the vertical part of the metric. Okay, the thing I wrote here is the vertical part of the metric. So we can prove easily that GF has this expression minus ax squared ddz squared plus lambda minus 2 times modulus a squared ddz squared minus a bar squared dz bar squared, where a is by definition one of the fundamental data I talked about in my first lecture, is the product of the immersion multiplied by the killing field. So it's the vertical part that you see in the surface of the killing field. Okay, so you have this expression for the metric of the projection. Okay, so what I'm doing now is to compute the eigenvalues of this metric with respect to the flat metric dz². Okay, I'm going to compute the eigenvalues of this. This is very simple, computing these eigenvalues, because you just have to take the determinant of GF minus, let's call it mu, identity equals 0. Okay, you compute the eigenvalues of this, and as you have an explicit expression, you can compute these eigenvalues in a simple way. So it turns out that you have two different eigenvalues. Mu1, which is lambda minus 4 times a squared, and mu2, which is lambda. Okay, those are the two eigenvalues. But now, from here, there is a condition, one of the basic conditions of the theory, that tells that 4 times modulus of h squared divided by lambda equals 1 minus nu squared, this thing. Okay? So if you write this thing down, it turns out that the first eigenvalue is actually lambda squared multiplied by lambda. Okay. So you have, this is the, and you have mu1 smaller than or equal to mu2. Okay. So this is the smaller eigenvalue, and this is the larger eigenvalue. But they are the eigenvalues of the vertical projection. So that is telling you that this thing is less than or equal than this thing, less than or equal than this thing. Okay, because the value of the vertical projection is always between the smaller and the upper eigenvalue. This thing we knew it was immediate, and this thing is actually what we wanted to prove, which is given by this. So that's the part we needed, and that gives you the existence. Okay, so let us prove now that this canonical example we have constructed are the, well, let me say first something. We can call it canonical examples because they can be classified. The 1-out theorem says that this harmonic map is unique. So in some sense, canonical example means that you have, that they are graphs for which this metric is complete. Okay? So the condition of being a canonical example is characterized by this condition, and moreover, all of them can be classified in terms of quadratic differentials. So for the uniqueness of these examples, the basic question, starting with Heisenberg, is if any entire minimal graph in Heisenberg is a canonical example. If we solve this problem, we have the uniqueness question we wanted. Okay, the main step to do this in Heisenberg, I'm going to write down now a lot of things in Heisenberg. I'm going to forget a bit about the rest of the critical CMC cases. So the key for doing this is the lemma that you have here. This lemma is saying something quite easy to understand, and it's the following thing. Assume that you have here a surface in H2 cross R. Then you can relate it by the sister correspondence to a certain surface, let us call it FA in nil3. Okay, F is the projection onto R2, and A is the factor I told before. Then you can do the following thing, and is that I'm going to put here the projection F as first coordinates, which takes values in R2, and I'm going to take here, well, with plus minus, the height function in H2 cross R. Okay, so this takes values in R3, because that takes values in R2 and that takes values in R. So I put here the metric not of R3, but the metric of Minkowski three-dimensional space. Then it turns out that this has constant mean curvature 1/2. If this has constant mean curvature 1/2, and if this is minimal. So this is very strange, because you don't have, well, strange, it's surprising, because you have two related theories. Minimal in Heisenberg, h equal to 1/2 in H2 cross R. Then you do the following trick. You take the projection onto the base R2 and you put it here, and the height function of the other theory, and you put it here. And miraculously, in some way, you end up having a CMC space-like surface in Minkowski three-dimensional space. Okay. Then the result is this one. that you have here. Okay, you have a surface of h equal to 1/2, its sister surface, then you take f as the first coordinate in L3 and h as the height function. This is a space-like surface with mean curvature 1/2, whose metric is this metric that is playing a key role for us, and whose Hopf differential is this thing. Okay, recall that the Gauss map of a space-like surface is harmonic. We said that in the previous day. So I'm going to say how this is proved. Okay, this lemma is proved. So I start denoting by lambda the common metric of the two sister surfaces in H2 cross R and in Heisenberg. Okay, this is the metric of these two surfaces. And I take the hyperbolic Gauss map of the one in H2 cross R. Let us call it G, and let us call Q its average Rosenberg differential. Then we know that minus Q lambda nu square are Weierstrass data for G. This is the theorem of representation. And moreover, it turns out that these two data, minus Q and lambda nu square, one can prove that they satisfy the Gauss-Kodach equations for CMC surfaces in L3. Okay, this is a computation coming from the harmonicity of the Gauss map. So you can prove that there exists a surface in L3 which has mean curvature equal to 1/2 and whose metric is lambda nu square and whose Hopf differential is minus Q. Okay, you have here a projection, you have here a height function. You don't know any of them at first. So I'm going to prove actually that if you move this surface, I mean this surface is unique up to isometry of L3. I'm going to prove that if you move the projection, if you move the surface in L3, I can make this projection go to where? To here, to the projection of the surface in Heisenberg, and this height function goes to the height function of H2 cross R. How do I do this? Well, one of the keys is this, and it is possible to prove that if you have a solution to the system for the height function, then you can prove that all solutions are of this form, f0 multiplied by a for some constant value of a. In particular, taking a equal to the identity, you can say that this, well, applying a rigid motion, you can say that the height function here agrees with the height function of H2 cross R. The system, I recall you, was, let me see if I can do this properly. Okay, this is the system. Okay, this is the system, and we can prove that solutions to this system can be explained in terms of surfaces of CMC in Minkowski space. And once we know this solution, we have the okay, I did it properly. So we know that this can be taken as plus or minus h at first. And now as regards for the projection, one can compute and say that the metric of the projection is given by this expression. Okay, this is just a computation. And now we take the metric in Heisenberg. Then we have this expression that I used for proving the estimate. And now I apply two things. One is the Benoit correspondence, which says that this thing goes to actually, A goes to minus h stat, minus I multiplied by h stat. So this changes sign here, and here I use again the same formula here. I deal a bit with it, and I have it like this. So I see that the metric of the projection in Minkowski space is the same as the metric of the projection in Heisenberg. So I compose with an adequate isometry again, and I see that you have the same. So this proves the lemma. And from this lemma, you can prove finally what you needed. Any entire minimal graph is a canonical example. Why? Assume you have an entire minimal graph. Then, as we explained previously, by the uniqueness of the 1-out theorem, it will be a canonical example exactly when this metric is complete. So I want to prove that that metric is complete. By the previous lemma, you can construct, associated to this surface in Heisenberg, a surface of constant mean curvature in Minkowski space, whose metric is given by this, and whose projection is given by f. Okay? But now, this metric, I want to prove that this metric is complete. If this metric is complete, it would be a canonical example. But now, the first surface in L3 is an entire graph, and it has the same projection here. So the surface in L3 is also an entire graph. And now you have the Chen-Yao theorem that Benoit also referred to, that says that any entire CMC graph in Minkowski space has complete induced metric. Okay, so you know now that this metric is complete, and this is what you needed, so it's a canonical example. So this can be seen as a consequence of the Chen-Yao theorem in Minkowski 3 space. So the classification that we obtain finally is that if you have a minimal surface in Heisenberg space, you have three equivalent statements. It is an entire graph. Its metric, associated metric given by the induced metric multiplied by the angle function squared is complete. And the third one is that it is a canonical example. That is one of the elements of the family that we describe in terms of quadratic differentials. In particular, you have a correspondence between the solutions to the Burstyn problem, that is the entire minimal graphs in Heisenberg, and the space of holomorphic quadratic differentials in the complex plane or the unit disk, when Q cannot be identically 0 in the case of C. Okay, so okay, this is the final picture in Heisenberg. Okay, so I want to realize now what happens for the rest of spaces. Okay, for the rest of spaces, you need a theorem by Benoit and Logan, which Benoit is going to expose in detail in his last two lectures, because it's a difficult theorem. The theorem of Benoit and Logan says the following thing. Assume that you have sigma, a minimal, complete in Heisenberg space, and you assume that it also has non-zero angle function. This means that it is transverse to the Killing field, or in other words, this means that it is a local graph. Okay, this condition means that it is a local graph. Then they prove that sigma is an entire graph. This is very non-trivial. Okay, this is very non-trivial. So Benoit is going to explain it. So from that result and the classification in Heisenberg, we can solve. I think I'm putting a bit crazy the camera because I'm moving a lot. So sorry. So we can solve the problem for all the values of the critical mean curvature different from minimal in Heisenberg. How is this done? Assume that sigma is an entire graph of critical constant mean curvature in some space. Okay, this is the definition of critical constant mean curvature. Then sigma is complete, obviously, because in a Riemannian space every entire graph is complete, and as it is also a local graph, its angle function is different from 0. These two conditions are preserved by the sister correspondence. Okay, so and by the sister correspondence, this surface, as it has critical mean curvature, corresponds to a minimal surface in Heisenberg. So its associated minimal surface in nil is complete and it's a local graph, or a multigraph can also be said. Okay, has these two conditions. So now you can apply here the Daniel-Hauswirth theorem, the theorem there. It says that under these conditions, this is an entire graph. Okay, how do you keep working with this? Once you have an entire graph, we know the classification theorem. The classification theorem says that something in Heisenberg is an entire graph if and only if this metric here is complete. So by the classification, mu square dd square is complete. For the minimal graph. But this thing, we said it was preserved by a sister correspondence. So the same is true for the original entire graph. Okay? And that's what we needed, because that means that's equivalent to say that this is a canonical example. So the proof is simple, taking into account what we have proved, that the entire graphs in Heisenberg are exactly the ones with this metric complete, and that taking into account the Benoit and Logan theorem. So the final classification theorem is the following one that is posed here. If you have a surface of critical constant mean curvature in any space, then you have three equivalent conditions. Either it is an entire graph, first it is an entire graph, second its associated metric is complete, and third it is a canonical example in the sense that it can be described in terms of the Abros-Rosenberg differential. So you have a correspondence between the space of solution to this Burstyn problem and the space of quadratic differentials on the complex plane or on the unit disk. So this is the final result of the case of Burstyn problem for all values of critical mean curvature. And well, I'm going to stop here. So thank you.